to my webcast on linear regression. Okay, so let's talk now about how we actually go about fitting a linear function to our raw data. Okay, so here we have the same, look at the same example again, so second year marks and third year marks, but now we're looking at our raw data. Okay, so we surveyed all of our third years last year and we looked to see what their second year mark was and what their third year mark was. Okay, now obviously normally you would have a lot more data than this. Okay, but to show you an example, it's just going to be easier if we just think about 4 data points. But the things I'm going to say would apply regardless of how many data points you had. Okay, so you would normally have dozens. Okay, so remember this is real data now. These are real data points that we've got from our survey. So these are telling us from our sample something about the relationship between our x value and our y value, something about the relationship between the second year mark and the third year mark. Okay, so what I'd like to do, what I want to do, what linear regression is going to do for me, is to fit a line to this data. Okay, I want to fit a line that describes the relationship between these two variables. And this relationship between the two variables is going to be defined by the actual data that I've got. So I'm using the data that I've got from real data that I've got. From that real data, I'm going to try and come up with a function that describes the relationship between the x and the y variable. What is that data telling me about the relationship between the x and the y variable? Okay, so remember, this is the equation we are using for linear regression. This equation here describes any linear function, any line function can be described by this equation. This is the equivalent of drawing a line. Okay, so remember what's going on here is we have y, which is the thing we're trying to predict. So whatever the value of y is going to be equal to x of the x-axis times the slope, remember b is a slope, plus a, which is the intercept. Okay, so what I want to do is to fit a line to this data, and then once I get a line fitted to this data, that line will have a slope value and it will have an intercept value, and I can then use those to predict the third year mark, or the y variable, from any x value. So I could find out what's going on here, or what's going on here, or what's going on here. Okay, so if you think about it, what we need to do here is we want to fit a line, but there's lots of different lines that we could draw here. We could have one here, we could have one like this, we could have one like this, we could have one like this. We need to decide what is the best description of our data, the best fit to our raw data points. Okay, so if we think about it, if you imagine we were trying to fit a line to this data, so here's our line we start with. If I increase, so this line is being described by this equation here, if I increase the value of the intercept, then it's going to make this line go up and down. If I increase the value of the slope, then it's going to make it, it's going to increase the slope of this line. So I want to come up with a value for the intercept and the value for the slope that gives us the best fit to this data. Okay. Now what we need to do is, when we have a line that we've come up with, which we think is the best fit, we need to see how much our model, okay, our lines are now our model, how much this deviates from our actual observed points. Okay, I want to minimise how different my model is from the data that I've got. Okay, so what I need to do is compare the difference between the prediction of the model and the actual data that I've got, the observed data. Okay, now just to make this a bit clearer when we get on. When we're talking about y values that are being predicted by the model, okay, so let's take this point here as an example. Okay, remember, if we want to give the coordinates of this point here. Okay, so this is a piece of data we've actually got. Okay, so we take the x value, which is around 70, and the y value, sorry, the x value, which is around 80, and the y value, which is around 70, approximately. Okay, so that's our observed value. Now, there's a piece of notation we need, which, so we don't get confused between the output of our model and the actual data that we've got. We put a little hat, and it's literally called a hat, on our y here. So our y here is what we're predicting from the model. Okay, so this point here would be what we're predicting from the model. Okay, this value of x, our model is predicting this value of y. Okay, so y with a little hat, that's what we're predicting from our model. Our observed value of y is y with a little I next to it. Okay, so if I subtract one from the other, that's going to tell me how much my model is differing from my observed points. Okay, so I'm going to have a difference between my model, the value my model is predicting here, and my observed point here. So that's going to be there's going to be a difference there. There's going to be a difference here between the model and my observed outcome. There's going to be a difference here between the model and the observed outcome, and similarly here. Okay, and the goal of our regression is to minimise these distances. Now, these distances, that are differences between the observed and our output from the model, are called residuals. Okay, so each one of these is a residual. And what linear regression tries to do is to try different combinations of values for A for the intercept and B for the slope, different values for our line, to try and reduce how big these residuals are. Okay? So you think, okay, well, all we need to do is each time we have a guess or we have a go at fitting the line, we just add these residuals up. Well, the problem with that is that some of these residuals, like this one here, this is going to be a positive difference. Okay, our y observed is larger than our y predicted, so this is going to give me a positive number. Okay, so say it's plus 1. Here, it's going to be a negative number. Our observed is less than our predicted from the model. So this is going to be a minus number. Similarly, this one's going to be a minus number. Let's put these values in here. It doesn't matter what the values are. It's obviously going to be a minus number here, a minus number here, a plus number here, a plus number here. So if we just added the residuals, then they will tend to cancel each other out. Okay, so if these are all equal to 1 but in different directions, our sum of the residuals will be 0. But clearly this line isn't perfectly fitting these points. So we need to take a slightly different measure which takes account of the fact that we've got some that are plus and some that are minuses, so that these residuals don't cancel each other out. And the measure we take is the sum of the squares of the errors. Basically, we just take each one of these and square them. Each one of these differences between our observed point and our predicted point from the model, the difference between here and here, we take each one of those and we square it. We multiply it by itself and we add those together. Okay, so we've got a minus number here. A minus squared is a plus, so minus 1 here will actually turn out to be our square of the residual. Our square of the residual will be plus 1. Here it will be 1 times 1, which is plus 1. Here it will be minus 1 times minus 1, which is plus 1. Here it's plus 1 times plus 1, which is plus 1. So that will give us a sum. If we added all of these together, it would give us something equal to 4. Okay, so that would be our measure of the sum of the square of the errors. Okay, and what linear regression is trying to do is to fit a line to these points that minimises this sum of the square of the errors. Okay, sum of the square of the errors is equal to our observed value of y minus our y from the model. Okay, and we're going to have this is going to be one of these for each of our data points. So it's going to be this plus another one for this one, plus another one for this one, sorry, and so on and so forth. For each of our observed values, we're going to have some residual value. So linear regression is going to try and fit a line to our data which minimises the sum of the square of the errors. Makes this value as small as possible. Once it's done that, it'll tell us what was the intercept value it had to use, what was the slope value it had to use in order to fit that data. So it's going to give us values to put into this equation. Okay, so it's going to give us something like, I don't know, 2 plus 3x. Okay, so that's going to define this line which fits our data with a minimal amount for the sum of the square of the errors. It give us an equation which minimises the difference between the outcome of this and our observed data. And in a nutshell, that's what linear analysis is. Okay, hopefully that's clear. I'm going to stop the tape again now, and then when I come back I'm going to talk about some other things that we need to bear in mind when we actually fit a linear regression to our data. Because there's a few other things that we have to look at, not just the output of the intercept and the slope. Okay, thank you. Hi, back again. Just before we continue, those of you who are paying attention carefully will notice I made a small mistake there. Now, each one of these should have had a square sign after it. So it's a sum of the square of the differences. Okay, I'll see you back in the next part of linear regression. Thanks.